Well, I expect there'll be a few stragglers arriving late, but we'll start anyway, conscious of the fact that everyone's giving up their lunch break, and I hope you enjoy what I've got to tell you. It'll be a bit different, I suspect. I thought at the start, it's not going to be easy to do audience participation. Is there anybody in the room who's never seen this picture before? No, I suspected not. I mean, it's one of the iconic images of the late 60s, early 70s. And the point of it really is that there are some of us of a certain age who remember a time before we'd seen this picture. And it's one of the paradoxes of the space endeavour is that as fast as we were all looking outwards and going out to the moon and going out to the planets, it actually gave us the opportunity to look backwards at the Earth. And a lot of people were left looking at this picture thinking, goodness me, what a tiny little thing it is. We better look after it. And I'm not sure we have, but anyway, that was just by way of a preamble. This was from Apollo 8, I think, and was at the early stages of the first circuits of the moon. In the summer of 1969, there was a lot going on. The Beatles held their last public performance. Woodstock happened, and by copycat, the first Glastonbury was the following year, realising that this was an interesting thing to have happen. The first Monty Python came out, so we're talking serious ancient history. The Hawker Harrier entered service for the first time, for the first commercial vertical takeoff aircraft. And I did the Grand Tour of America on the Greyhound buses, which took me to Cape Kennedy on July the 15th, 1969. It's taken me 40 years to work out where I was, actually watching the rocket take off, about 10 miles away, looking over the swamp at the launch tower in the distance. At about 9:30 in the morning, we saw the rocket take off. This is synthesized. My pictures are all on 8mm movie, and I've never worked out how to convert it to video yet, one day. The rocket took off in absolute silence. I mean, the whole of the coast was sort of packed with people. One of my abiding memories is a little aeroplane flying over and spraying everybody with insecticide, which sort of seemed like a nice touch, I suppose. But it was... well, at least they cared about us. But the rocket took off in absolute silence. It had got to about this point in the sky when the noise hit everybody. And it was the loudest noise I've ever experienced in my entire life. And one felt one was going to be pushed off one's feet. I think people who have watched the shuttle take off have heard the same thing. It was absolutely phenomenal. And it took that long for the noise to come across the 10 miles and hit us. It was absolutely phenomenal. So that was Apollo 11 taking off from Cape Kennedy. July the 16th, on 40 years ago today, the first moon landing. Neil Armstrong set foot on the moon for the first time and essentially made history. For me, I realised at that point that maybe there was a future in astronautics. I'd been studying physics at university on the advice of Sir Bernard Lovell and Patrick Moore, with a view to possibly becoming an astronomer, decided that maybe astronautics was a possibility now, and went to work at Hawker Siddeley Dynamics, and this is one of the satellites I worked on, Miranda, as a thermal design engineer, which was why I later made to get a job in fire research. But this, it was one of these projects which was a bit depressing in that it just took like forever. It never actually got launched until after I'd left Hawker Siddeley, and the workload, the task was so complicated that it all got sliced into such tiny slices that any one individual slice was so small that essentially you bored your socks off, candidly. It was in the early days of computers as well. We did have computers. In fact, at Hawker Siddeley, we ran a bureau service using the spare capacity of the computers we had. They were so powerful. Something that will strike a chord these days is that the bureau service became so profitable, it then became difficult for the aeronautical engineers to actually get time on the computers. But they managed to get through that. It was great innovation. We actually had some Hewlett-Packard calculators in the days of reverse Polish, if anyone's old enough to remember reverse Polish. They were interesting to use, but that was the sort of technology we were using in those days. But the work we did with BRE was in connection with the Columbus project. The history of this is that at BRE, we had been involved right from the inception of the Channel Tunnel project. And we'd been providing fire engineering consultancy and fire safety consultancy to the Channel Tunnel Safety Authority. Now, in 1992, the then chairman of the fire working group of the Channel Tunnel, Safety Authority, but was invited to the European Space Technology Centre to give them a talk about fire safety in the Channel Tunnel. And it was the chief officer from Kent at the time, Jeremy Beach, and realising that things were going to get extremely technical, he asked myself and a colleague at the time, Peter BRE, if we would go with him to help fend some of the technical issues related to fire safety in the Channel Tunnel. And the reason for this was that the Columbus project, which I'll say a little bit more about in a minute, was the first vehicle that the European Space Agency was involved with, which was actually a manned vehicle. And so there was no history within the Space Agency of dealing with manned vehicles, dealing with the safety issues that went along with that. And so it was all a bit new to them. They were getting worried they weren't all speaking the same language, particularly in relation to fire safety. And so that's why they thought the Channel Tunnel was sort of a bit like a space capsule. It was like miles from anywhere. You didn't have the fire brigade. You had to be self-contained. And that maybe there were sort of parallels that would help get them up to speed with fire safety on the space station. So the two of us went out there with Jeremy Beach. We gave a presentation to them of fire safety in the Channel Tunnel. We got taken for a tour of the museum, which included a little seaside thing that you could put your head behind. And at the end of it, we were asked to assist the project in two regards. Firstly, in looking at the fire safety strategy for the Columbus module, and secondly, to actually carry out some fire experiments in microgravity, which all sounded good fun. A little bit about this International Space Station. I won't go into too many details. It is a big project. The Columbus is, again, a consortium project, over 40 firms involved. It's 13-ton space laboratory, 4.5 metres diameter, 75 cubic metres of working space for scientific instruments. So essentially a laboratory, they're going to be put up there. And the way it's working is that there's payload racks, and so you can send up experiments as a payload rack in later shuttle flights, and they can be plugged in to the modules and used. And it's a completely autonomous unit, a part of the space station. So here's some pictures of it. You see it's a fairly chunky little lump. It is plugged onto the space station with its own power, and you can see it's supposed to be a sort of shirt sleeves environment. Lots of different experiments going on into the laboratory. Main issue is it has to be protected against meteorite impact. It has to obviously plug onto the other international modules attached to the space station. Some of you will be aware, in fact, I think last weekend, the Japanese module successfully got taken up to the space station, which is, again, part of the assembly that's going on up on the space station. That's an outside view of the various elements that they have. Now, the history of this, as I mentioned, is that the Space Agency had no history or experience of manned spaceflight. They've certainly got no expertise in fire safety. I don't think they've got much expertise on fire safety on the ground, let alone in space, but that's another story. The Americans were completely dominating any discussions of fire safety. The Americans had the Apollo 1 disaster and were totally neurotic about fire safety, which perhaps with good cause, but nevertheless they were very much dominating the discussions and were, in a sense, preempting the European engineers' opportunities for deciding on their own fire safety strategy. So the Space Agency wanted its own independent review of fire safety. The sort of issues that we were being asked to look at was the detection of fires in microgravity, what their response procedures ought to be if there was a fire, whether it's possible to use a suppression system or indeed whether you could just open a window. The Americans didn't like that idea. The Americans said that if you opened a window and let all the air out, well, this wasn't too good for the people on board, of course, but that was a separate issue. But they thought that the rush of air venting into space would actually make the fire flare up. We weren't so sure, but nevertheless, that was one of the issues. And the sort of problems they had, we said, well, why don't you just ban combustible materials? Oh, they can't do that. The astronauts are up there for years at a time. They've got to have their teddy bears and their guitars and their other personal belongings. Well, okay, I suppose there might be a business in producing non-combustible teddy bears. Perhaps we ought to think about that. I haven't gone there yet. There's no fire brigade, a bit of a long way away. And you can't really abandon the ship, can you, really? There was, all you could hope to do was isolate modules if there was a fire. So they were the sort of things. But the bottom line really was, what does a fire do? How does it grow in zero gravity? And how does it spread? How does smoke spread? They were the sorts of issues. This is the pictures of Apollo 1. A lot of you here weren't born when this happened, but it was the first planned launch of the Saturn rocket with the Apollo module, and they were running it on 100% oxygen, at low pressure, 100% oxygen, and there was a fire on the launch pad, and all 3 astronauts died. Caused a bit of a glitch in the space program, bearing in mind that from Yuri Gagarin's launch to landing on the moon was less than 10 years. So as glitches go, it was a pretty quick glitch. But nevertheless, it was an issue. So from our point of view, the way the Columbus was set up was you had these experimental racks, these which you then put into a unit, which then itself fitted into the laboratory. And quite a nice idea. It does sort of limit you a bit in the size of experiments you can do, but it does give you enormous flexibility, and it means that experiments can be taken up and brought down again. You can send up materials, bring them back after they've been exposed to the zero gravity environment. But on the other hand, you had to have a cooling system, you had to have power. There were issues about the potential development and spread of fire. Now, when it came to actually doing fire experiments in microgravity, again, the Americans were very dominant. They'd done some experiments on the shuttle, very limited. They'd done experiments in parabolic flight, and they'd also done experiments using drop towers. So there was some experimental data around that they were using as the basis for their own strategy. But a lot of those experiments were very academic, very much looking at combustion processes from a very scientific point of view, rather than, if you like, the sort of more prosaic issues of just keeping the astronauts alive if there was a fire. Again, the Space Agency wanted its own research in order to balance discussions. They wanted their own research papers that they could put on the table with the Americans and have a basis for a sort of a balanced debate on the discussion. Certainly the European astronauts were concerned about fire. They'd been listening to the Americans, and the Americans were giving them the jitters about fire. They'd somehow got this idea that any fire in space was going to be an immediate disaster. They had done some tethered experiments. This is where the experiment is essentially on a sort of a semi sort of mobile arm attached to the aircraft under parabolic flights, which was essentially burning candles, which was sort of useful up to a point, but only took you so far. So what we were being asked to do is, first of all, to design and construct a free floating fire experiment. The idea of a free floating fire experiment was a bit novel. We were to construct and commission it, and we would then fly with it on the next 2 parabolic flight campaigns that were planned by the Space Agency, at which point we suddenly thought, this conversation has gone in a slightly different direction from that we expected. We thought we were going to help them do these experiments. Suddenly they're expecting us to be there with it. Oh dear. Right. Interesting. This is the so-called vomit comet. They're all called that, whether they're American or British or Russian, because it's an accurate term. The flight path, which I'll explain in a minute, basically takes the aircraft for a short period of time down to what's called microgravity rather than zero gravity. For various reasons, the aircraft, when it's in zero gravity, has a drift, a slight drift along the length of the cabin. And the idea is that if you've accidentally left things lying around in the cabin, pencils, nuts and bolts, screwdrivers, or bits of wire with crocodile clips on the end of it, these might drift into the cockpit and cause a bit of a problem. So they try to maintain a gentle drift backwards down the plane. But essentially, this is the plane just about to enter the parabola, and so it does actually go off at this angle for a short while. The way it works is that the plane starts off at around 20,000 feet at 1G. It then pulls up at about 45 degrees, during which time you experience 2G. And it then goes over the top of the parabola, during which time you get essentially the microgravity. And that lasts about 20 seconds, and then you have the pull-up for another 2G for another 20 seconds. And then we were very kindly given 2 minutes to get everything ready for the next experiment. So it was absolutely frenetic, as you'll see in the video in a minute. Absolutely frenetic. It's been suggested to me, this is a bit like in a much larger scale, taking your car over a humpback bridge, just for those few moments when you leave your seat. It's just imagine that lasting 20 seconds. That's what it's like. It's essentially the same process. You and the vehicle you're in are both travelling in the same trajectory, so there's nothing to stick you to the floor anymore. Okay, so the objectives of our project. First of all, there was the intention to give the astronauts that travelled with us direct experience of flames. As I mentioned earlier, they were absolutely paranoid about fire, and they couldn't really believe you could have a fire in zero gravity without it being a disaster. So partly the idea was to just have some flames and let them see them, which is funny when you think about what happened later, but we'll tell you about that. So basically that you could handle fire in zero gravity. It wasn't a complete disaster. Have video of it, test the effect of different sorts of materials, different sorts of fuels, look at the effect of an airflow. I mean, one of the issues was, of course, that on the space station there's a constant flow of air to allow the astronauts to breathe, so that may have some effect on the fire. We do some measurements of temperature, optical and other detector outputs that we might be able to record, and then basically to produce the Space Agency's own research findings. So the free-floating fire experiment was a bit of a rush. It was built in what was then the Fire Research Station's workshops by our own craftsmen. Extremely fast construction. I'll show you some times in a minute. It had to withstand 9G. Seems quite sort of measly little for G-force really, considering what the airplane would do if it crashed, but it wasn't supposed to crash. This was so that if you just bounced around a bit, it wouldn't fall apart. Had to be safe. There was a lot of effort went into making sure that we wasn't going to explode on the aircraft or cause any other sorts of damage. What that meant was, though, we had to make sure it was fully padded. It had to be fitted with a fire extinguisher. We had to be able to vent the smoke from inside the chamber, and we actually fitted an explosion relief system, which we weren't expecting to use. It was fitted with video camcorders. The state-of-the-art camcorders we used at the time were little Sony camcorders. One of the reasons for choosing them rather than anything more sophisticated was that we worked out that these cameras were designed to be used by 3-year-old children, and we all know what 3-year-old children do with things, like throw them across the room. So we reckoned that if anything was going to stand up to 9G, an ordinary off-the-shelf Sony camcorder would, and it did. We had to provide fans to produce the airflow. We had to have changeable burners to try different fuels, and it all had to be remote because the rig was going to be floating in microgravity. We had to be able to operate it without having to touch it. There were 2 flights in all. In the second flight, we were able to fit the rig with thermocouples and sensors. So some of the pictures you'll see from the first campaign where there weren't any sensors, and then some from the second campaign where we had thermocouples and other sensors fitted. Now, as far as we were concerned, actually taking part in all this, if anybody watched the James May programmes earlier last week when he went on the U2, it was the same sort of stuff. We had to have a Class 1 medical certificate in order to go on the flights. We had to have hyperbaric chamber experience. We had to have an understanding family, it goes without saying. I don't think we actually needed any Valium, but I think there was some on board. And then we had to transport the whole lot out to a military research base in France where it was loaded onto the plane. And it was a converted Caravelle that was used for this. For the first first series, myself and Peter Barry and Peter Fardelli, in fact, has joined us today, and another colleague came with us to help with sort of ground support, as it were. And so the second campaign, it was just myself and Peter Barry who went on the flights. We were experienced by then, so that was easier. The programme, the way it worked out, I mentioned already, it was in January 92 that we first went to ESTEC. By February of 92, third week of February, we'd had contact with the Space Agency. That should say contract. We actually had a contract with them. And by March 92, the second week of, we'd actually participated in the first series. So it was pretty frenetic. It'd be nice to think we could still do it today, but by the time we'd done our safety memos, I'm not sure we would. What were the design constraints? I've already mentioned it had to be safe. We weren't going to blow up the plane. It had to be ready by the 10th of March 1992. This was not negotiable. That's when the plane was going to take off. We were either going to be there or not be there. It had to be compatible with the other experiments in the aircraft. It had to weigh less than 25 kilograms. Had to withstand 9G. I've mentioned that. It had to fit through the door of the aircraft, which itself imposed some limitations. Had to cope with the pressure equivalent of 70,000 feet. Although it was a pressurized aircraft, it was at lower pressures than normal. And we couldn't have fumes escaping into the cabin. They'd had a bit of a crisis on an earlier flight where somebody could smell burning for some reason and yelled fire and caused absolute panic, and they really didn't want that happening. Each fire was only going to last about 20 seconds. We thought, in practice, we didn't actually get continuous 20 seconds of microgravity, but As you'll see later, that wasn't really an issue. And we had 2 minutes between parabolas to prepare for the next parabola. So that was, as I say, not a lot of time scrambling around on the bottom of an aircraft. So the final design, we came in at 24 kilograms. We finished up with approximately half a metre cube padded. You'll see pictures in a minute. The actual test chamber was about 0.3 of a metre cubic test chamber. We call it 0.3 of a metre. It was actually a foot cube, for those of you who are old enough to remember what a foot is. But that was where it came from. We happened to have a box that size, and it seemed to fit. We were using butane as our fuel, primary fuel, although we did also have paper. We had to fit up a little spark igniter so we could ignite the material as we went into microgravity. We had a selection of burners. We were burning gas primarily. We also had a burner which would hold paper, and you'll see pictures of that later, and we had this unpronounceable chemical to try as well. We had fans in the rig to create an airflow across the test chamber. We fitted it with various instruments. We had a multi-gas analyzer for measuring CO. We had a CO2 sampling line in the first campaign running to a gas analyzer. I think we abandoned that for the second campaign. It was causing too much drag on the test rig. And we actually had to fit a water extinguishing system. Now, this was interesting in itself, because if you think about how a normal water extinguisher works, you have water in the bottom and pressurized gas at the top, and when you release it, the pressurized gas pushes the water out. In zero gravity, it doesn't work like that. The whole thing turns into a nice air-water froth and wasn't going to do anything. So what we had to do is actually design and build our own fire extinguisher, which actually involved having a diaphragm that was pressurized, and that actually pushed the water out, so you kept the air and the water separated. There was an interesting story about people opening bottles of champagne in zero gravity and getting this funny squirty snake of froth coming out, and that's not what we wanted from our fire extinguisher. And we fitted, as I mentioned already, we fitted an explosion relief vent just to be on the safe side, and we had to have a purging port, which there's a story about as well I'll come to. As far as the Class 1 medical certificate, this was all the stuff we went to. I don't think I've been probed and tested quite as thoroughly either before or since. They did the EEG, which I've never had before. The thing I always remember about that was the nurse sticking these rather sticky little electrodes on my head and saying to me, "Have you ever fainted before?" I thought, what do you mean before? What's that mean? But it's an epilepsy test, so fortunately I passed. But well, I guess we all passed. But it was fairly thorough. We finish up with the same sort of medical certificate that you need if you're going to pilot a jumbo jet. So that was quite nice. Unfortunately, it's expired now, but then I'm a lot older, so that's to be expected. But the other thing I mentioned, we had to have hyperbaric chamber experience. We managed to track down the place where we could do that at the Institute of Aviation Medicine at the time at Farnborough, who offered to do it for us. I don't know whether we ever paid them, I can't remember, but they seem to think it was all a bit of novelty. If anyone's familiar with these things, I mean, it's the same sort of chambers that are used to divers and so forth, but in this case they suck all the air out. And the idea officially, if you were going to be a pilot of a plane or do anything really safety critical, they would keep sucking the air out until you fainted. Our doctor said, well, what's the point of having you faint? You're not going to learn anything while you're unconscious. So he decided that there wasn't really the point in going to the full decompression. But nevertheless, we did go up to the equivalent of quite a high height. And the other memory I have of that, I don't know whether Peter will remember, was that our colleague Peter BRE had a beard at the time, and these oxygen masks would not fit. And so the doctor was tightening the straps, and he was getting redder and redder, and eventually I managed to get a good seal. But that's a lesson for you. If you've got to wear an oxygen mask in anger, don't have a beard. What else? So we got a letter of approval from the Institute, which allowed us to fly. So this is the rig being developed. This is the 1 foot square chamber that was our original test chamber. These are the guys from the Space Agency who came to visit to see what was happening. That's John Rowley. I don't know if he's here today, but he was, some of you know John, he's still here and was active on the project. This is the rig that we eventually built. Interestingly, we only ever drew up the design drawings after the project. At the time, we were making little cardboard models, and the guys in the workshops were building it from scraps in their toolbox and so forth. So you can see a fairly complex piece of equipment, considering it was really only built in about 3 weeks. Let's say a couple of commercial camcorders. Wherever we could buy stuff off the shelf, we were buying stuff off the shelf. The padding was essentially plumbing insulation that you can just buy in a hardware shop. The colour chart that we used was just cut out of a Dulux colour chart. We just sort of threw this thing together. not without its trials, but it all came together, and you can see the rig on a trolley there. These are the different burners we had at different times. The basic burner in the middle was the one that we used for the first campaign. As you can see, the whole thing was fitted with a keyhole slot, so we could just change burners very quickly in the 2 minutes that we had available. For the later campaign, you can see we fitted a little thermocouple column, and we also had, from the earlier tests, we had a little paper holder and the chemical that we were burning as well. So it was all sort of designed so we could just open the door, change the burners between parabolas. This is some of the other equipment. We had these little fans built into the roof plenum to allow us to produce an airflow. For the later experiments, we had a little smoke detector and other sensors built in. And for the butane, we bought a whole lot of CO2 cylinders off life jackets, which we then had to empty and replace with butane. And what was fascinating was that as well as the gas cylinders, you could actually buy a special gas cylinder popper in order to do that. So they were, I can't remember, we had about 20 of those cylinders built into the test rig, all full of butane. It meant we could switch them on individually. It was one of the safety measures, was that we could switch the butane on and off as the experiment progressed. So this is the rig on it's being developed, and here it is being test run in the lab. And you can see how big the flames are. Not really very big, like little Bunsen flames. That's all we were hoping to achieve, given the constraints that we had. This is us in the car taking it out to France. A lot of equipment. We nearly got arrested trying to get on the ferry because we had a gas cylinder in the back, and you're not supposed to have gas cylinders on ferries. And then it all got very anyway, we managed to get across to France anyway, not without some trial. So this is the Caravelle. You've basically a standard Caravelle, but fitted out for microgravity, zero gravity flight. I mean, most commercial aircraft can cope with zero or negative gravity. That's so that if they actually stall and start falling out of the sky, they can actually power out of the stall, which of course, if they weren't equipped for that, if the fuel just started sloshing around in the fuel tanks and not going to the engines, they wouldn't be able to do that. So more or less any plane flying can do parabolas. The difference is that these are fitted out for actual experiments, which means you essentially have a lot of padding. The seats are only at the back. You have nearly the whole of the working space is taken up with just a big empty compartment. You have netting and in order to stop things drifting out of control. Smoke masks are distributed along the whole length of the aircraft. So this is our rig strapped down, ready for the flight. You can see we're just one of the experiments on board. This is our crew. We all had to be kitted up in Nomex flight suits. I mentioned Peter Fardell, Peter Bow, and myself on the aircraft. Now this was when we came to the second series. We were using an old BBC computer to do the data logging, and when we tried to work out how we were going to work this on the plane, bearing in mind that we needed to start operating the computer while we were actually doing the 2G pull-up, we realised that this wasn't going to work too well under normal use. So we came up with a highly ergonomic way of doing this, where everything was essentially upside down. So you'll never see a computer like this before, with the keyboard on top of the computer, on top of the screen, and used by somebody actually lying on their back, looking over the top of their head to actually operate it. Not recommended, I have to say, but it worked. Oh, and that was an Acorn. My apologies for those of you old enough to remember what they are. Probably got. I don't know. Has it got less power than my pocket calculator? Probably has, but it was certainly it was state of the art at the time. What the heck? There were other experiments on the plane that we were having to share with, at least on the second campaign. Somebody was looking at the fertilisation of frogs' eggs. I mean, this is obviously extremely important for the astronauts to understand this sort of thing. Somebody was looking at what they called monkey grip shoes. There was one of the issues about being in space, of course, is that if you want to tighten up a nut on a bolt, you start turning and the bolt stays still and you start spinning. So there's all sorts of different technologies being introduced to try and make sure that the astronauts can stay stuck to the floor while they're actually doing things. And the monkey grip shoes were one of the things. It was like having little grabbers on your shoes, so you could walk around like a monkey grabbing the branches as you go. So there were other experiments that people were trying out all over the place. This is some of the other experiments on the plane. So we were having to share all this space, which again put constraints, because you can see our rig there at the front. We couldn't allow it to drift too far up and down the cabin because there are other people working. Okay, so there were a few highlights to this. Anybody who's watched Star Trek knows that English is the universal language. Well, it is. Everyone spoke English, even the French, through gritted teeth, but they did, which made life a bit easy for us. So that was quite convenient. They did recommend taking water on board. They recommended not taking food on board. We had French paratroopers as a cabin crew, which was entertaining in itself. If you imagine, 1 minute they're fighting in Algeria, the next minute they're babysitting us. Our other colleague, Peter BRE, used them quite a lot. He was a keen sailor. In fact, he did training with the Civil Service Sailing Club, but he also tended to get seasick very easily. He was able to carry on working despite being seasick, or in this case, space sick, I suppose. And so there was a wonderful scene that we remember of him working away, throwing up, carrying on working, and these French paratroopers bringing him sick bags during the flight. Anybody who watched 2001: A Space Odyssey will remember that everything was stuck down with Velcro to stop it drifting off in zero gravity. Well, that's what we used as well. So I'd got pencils with bits of Velcro, notepads with bits of Velcro. Everything had Velcro all over it, and you just stuck this stuff around you to stop it drifting off down the cabin. And things did. I have an abiding image of one of our burners, which between two parabolas, I'd tucked the burner into my flight suit. That's while I was working. And then we went into the parabola, and I looked up, and this thing was drifting off down the cabin. And Peter BRE, our colleague, was sitting at the rear of the cabin, and he snatched it out of the air as it drifted past. Very surreal. What else? Oh, we had our own oxygen masks, so we had to have training in that. We had our own flight suits. The astronauts on board were exempt from that and caused a bit of fuss, but they were going to wear their own flight suits. We were offered motion sickness prescription before we took part in the flight. I think most of us decided that was a good idea. But in fact, we had a doctor on board, which was sort of worrying in a way, but sort of reassuring and worrying at the same time. They've never been on a flight which actually has its own doctor. What else? There were limited facilities on board. To this day, I don't know what the girls did, but that's what we were supposed to do. Thank God, never tested it, I have to say, but never mind. What else? We had test pilots and astronauts flying the aircraft. It was a bit like, I don't know, I suppose a bit like doing the Trans-Sahara Rally. They would just decide they were going to swap over mid-flight. Oh, do you want to take over the controls? Oh, yeah, thank you. That's fine. Okay, so that was all right, but I guess, well, if you've been on the shuttle, then flying a Caravelle was a bit of a doddle. Each flight lasted about 2.5 hours, roughly. You would take off from the base, fly out to what they called the box, which was the airspace allocated by air traffic control, and then you would spend about 90 minutes doing parabolas, 30 parabolas in all, and you gathered 2 minutes between each parabola, and then about 30 minutes to return to base. So fairly hectic. Bit scary. Once the doors closed on that airplane, that was it. You were there for that 90 minutes. Sorry, that 2.5 hours, you weren't going anywhere apart from closing your eyes and wishing to die, but that was the choice. We did manage to have an explosion. We did successfully vent the test chamber. They provided us with a pipe, which between parabolas, we would put on the back of the chamber to vent the smoke out before we opened the door. It took me a little while to realise that while we were venting this chamber, one of the officers up in the cockpit was busily repressurising the cabin. We were actually depressurising the whole of the aircraft with this tube. It took me a little while to work out this wasn't just like a vacuum cleaner. This was actually connected to the fresh air outside the aircraft. We had a bird strike on one occasion, which caused a bit of excitement, particularly. It was then followed by a stall warning, so that caused a bit of a scare. And on that particular flight, the aircraft returned back to the base, and they checked the aeroplane out while we had our lunch, and then we took off again in the afternoon to finish off the experiments. But being in zero G is a bit weird. Some of you know I'm an artist in spare time, and drawing astronauts in zero G was always one of the things, you're making them like ballet dancers drifting through the sky. So it wasn't like that. If you think about when you're in 1G, everything's stuck to the floor. When you're in 0G, it's not just that you're floating, but sort of like everything's floating. Like you're floating inside, your hair's floating, everything's floating. It looks absolutely shambolic. It really, and it's worse than that, because if you think about the average human being, most of us come equipped with some innards. Now, when you're floating around, your innards decide they're going to float around as well. Which, by repute, it does cause some interesting features, but I have to be candid, I never really experienced it, but rumour has it it can be upsetting, but that's the reason. Never really thought about it. When you swim, of course, it's not nothing like it, because when you're swimming, the whole body's being held up by the water, whereas in zero G, everything's just bouncing around. All right, what else? We had a couple of European astronauts on board. There was an astronaut corps had been in business for some time, but of course flying with the Americans, and I guess some of them had flown with the Russians. Ulf Merbold flew in 1983, and of course flew a bit later. They were both on the flight with us. Of course, had taken quite an interest in fire safety, and he came to a lot of our briefing meetings. Merbold was one of the guys who took over flying the plane just for a bit of fun. Outcomes. Well, on the first series, we're on the 10th to the 12th of March in 92. As I mentioned before, there were 4 of us there. We managed to complete 101 parabolas, carrying out 46 fires at one explosion, which wasn't planned. The second series, just the 2 of us, we'd added some instruments, including taking on some bladders of oxygen so we could increase the oxygen concentration. We managed 90 parabolas during that campaign, but with 60 fires, and 38 of them we managed to collect data. So that was quite a good hit rate, I think. We were quite pleased with that. So let's see if I can get the video to go. Yes, it starts off silent. So this shows this is some animation. In fact, we're told, I don't need it now. We could have pictures of the real space station, but this is an animation that the Space Agency provided us with, showing how it was all going to come together. This shows the various data, equipment racks and experimental racks that were all going to be fitted in to the laboratory. So you can see quite a complex. I mean, one of the things that's amusing is that they do try to maintain an up and down. They figure that the astronauts get very confused if you have everything higgledy-piggledy. So one of the surfaces is defined as being the floor, and another surface is defined as being the ceiling, and you're not supposed to walk on the ceiling. It's one of the rules. So there's the aircraft taking off. This is us on board. So they're my socks you can see there, attached to my feet, I hasten to add. And you can see all the other experiments. This is our rig in the foreground. We're in the control cabin looking back. Here we are now. Remember, the aircraft is going up at 45 degrees here. And then we come into the parabola. Now you see why it had to stand up to 9G. The regulars in the Space Agency, they made a big macho thing of not having to sit down during the 2G. They would just stand there, look very bold. So here was our flames. That noise is a little gas warning buzzer we fitted after the first campaign. There we see the flames going into microgravity. And you think it's gone out. The first time we thought it had gone out, but it hadn't. This is one of these samples of paper. We used the filter paper because it's clay-free. Okay, so this is some of the more technical stuff we presented for the Space Agency. So what we've done here is we've taken all 3 views off the cameras that we had. So we've got the 2 views for the 2 cameras, so we're getting 2 different views of the flame on the 2 top. We've got the view in the cabin, and then we've got our data record. And what you see is that the flame fluctuates as the rig bounces around the chamber. you can see the rig fluctuating, but also the signals we were getting on the various sensors were changing as well. You'll be aware that the French crew are completely oblivious to all the work going on behind their backs. Okay, and lastly, this is just for your amusement. This is, well, you'll see what happens here. We're releasing gas ready to go into the parabola. Oh no, we weren't releasing gas. We thought we weren't releasing gas. We were releasing gas. That was our explosion in microgravity, which was not to be repeated. And were we pleased we put in an explosion relief vent at that point when we... but basically we'd been releasing gas. We hadn't realised we were releasing gas, so when we went to ignite the gas was already in the chamber. Interestingly, I mean, the main thing that you notice about an explosion is that explosions don't care about convection. They just get on with it. So an explosion in microgravity looks just the same as an explosion anywhere else. Okay, so that's the video. A few stills taken from the flights. On my the first parabola of any flight is just sort of acclimatization. The guys insisted that I sit cross-legged on the floor and just drift away during the first parabola, which was sort of a bit scary actually. It was quite pleasant being in microgravity while you've got something to hang on to, but just drifting sort of loose was a bit weird. But then this on you can see us operating the rig and the computer operator working there. So more pictures of the flames. You see again the spherical flame that we got from all the sorts of fires that we were burning. This is typical of the data output we were getting. We were measuring a whole range of different sensors, thermocouples, and interestingly you see that some of them, the temperatures went up as we went into microgravity. I'll explain a little bit about what we thought was happening. So a lot of data that we were collecting from there. But a little bit about the science of all this. For those who are not familiar with fire, in a nutshell, basically you need a source of thermal radiation to warm a surface up. This gives off volatile gases from the material which rise under convection. And then if there's an ignition source and a supply of air, then the volatile gases burn, and it's the burning that causes the flame. You then get heat feedback to the surface, and the whole lot goes up because you've got warm gases in the cold atmosphere, and under convection, due to gravity, the gases rise up. Because they rise away from the flame, they cool, and you may get incomplete combustion, and we get soot particles left, and the soot particles form the smoke. Very simple, that's what a flame is. And you're in microgravity, you still need a source of radiation, you're still going to get the volatile gases, but they're not going to rise, they're just going to cluster around the material. You then bring in air and an ignition source, and they carry on burning, but now there's nowhere for them to go. They're not going to rise, they're just going to sit there. And so what happens is they just carry on burning, moving outwards from the source of fuel, and burning in a little blob with nothing to lift them away. And so this is what we think is happening here, which is why if you were to actually blow air over this, you actually get the same effect as you would with convection. You get forced convection instead of natural convection. And so the wind-blown flames looked almost exactly like ordinary flames. So that's the basic principle of where we'd got to with this. So what are our findings from the project? First of all, we were able to show the astronauts what flames look like in microgravity. We were able to show them that it could be done safely. We had this point that the flames became spherical, which we sort of expected. What we didn't really expect was that they became invisible. That was a bit of a surprise for everybody. But we could still detect the flames with some of our sensors. We could still measure that they were still burning. There was still a temperature to measure. We could still detect them on some of the infrared or ultraviolet detectors. On solid materials, the flames eventually did go out, but not on the scale that we were using, and wind-blown flames would behave like normal flames, which really was quite reassuring, because what that meant was that on the space station, where you've got a constant movement of air, as I mentioned, probably they're not going to be getting these invisible flames, but they need to be aware of the possibility. The reports, we produced 2 quite large reports for the Space Agency from each of the 2 campaigns. A number of publications came from this work. A paper that we were able to give in a conference in Ottawa, later on another paper in Moscow. It was quite interesting that the Russians were actually interested in what we were doing in space research. It was quite reassuring. Other papers were produced from the project. We've been quoted by NASA in a number of NASA papers, both by the Americans and the Russians, so it got out. Other things that have happened since, there was a fire on Mir in 1997, where they clearly had a bit of a fire, but nobody was injured, although it did require them to wear respirators. Some fire experiments were planned on Columbia in 2003, and I think those experiments were carried out, but as most of you will recollect, Columbia never actually made it to was lost on re-entry. So I think that the experimental results are maybe still available, but obviously that was a bit of a tragedy. The space module itself, Columbia, was completed and was moved out to America by plane. It was launched on February 7th, 2008, which is when I originally gave my shortened version of this talk, and was successfully connected to the space station. That's the crew. That's the Columbia being launched, and this is Columbia being bolted onto the space station. So only 15 years after we did our work with them, they finally got the thing up there. It was all delayed, of course, by the difficulties with the space shuttle. But now it's up there and it's being used. So I hope they don't have any fires, but perhaps if they do, we'll find out about it. So some lessons from the project overall, take us all a bit down to earth. It was quite stimulating working to an absolutely non-negotiable deadline. That aeroplane was going to take off, and we were either going to be on it or we weren't going to be on it. We did not have any room for negotiation on that. We just had to work and make sure it happened. We had well-defined objectives. We knew exactly what it was that we were trying to achieve. We knew we had well-defined goals. We knew how we were going to go about achieving the objectives, what we had to do to be on that. It did need quite precise project management to make it all happen. There was a big team of people all working together to get this to put together. Did require a lot of teamwork. Did require a lot of support from management. It required a mix of skill, different people doing different things, all coming together to make all this happen. It was a matter of making sure that people who's had got particular skills were being exploited in the right way, and we all worked together as a team. But it did require a lot of commitment, it did require a lot of overtime, it did require a lot of bought-in pizzas, but nevertheless that was the sort of commitment that people made, and I guess it was quite an exciting project with a hint of danger, which did add a bit to the whole thing. I think the main thing was that it was an opportunity that we were presented with that we really weren't going to let slide, and we consider, even now I think we were quite privileged to have the opportunity to do that. Right, that's it, thank you. So, I don't know if anyone's got any questions, but I have to say it's all very nostalgic and that, and my brain's gone soggy, but if anyone's got any questions, I'll attempt to answer them.